Friends, welcome to another class. So today we'll be again continuing from the from solving problems on the back of the chapter. Today we will solve problem number 2. So it is given as examine the significance of the stress function c theta, where c is a constant. Apply it to a ring A less than or less than B and to an infinite plane. A ring is fixed at R equal to A and subjected to a uniform circumferential shear at R equal to B, forming a couple M. Use equations 49, 50, 51. Using those equations, find an expression for the circumferential displacement B at R equal to B. Okay, so there are two parts for the question. So what you are given is you are basically given in a stress function. So the stress function is C theta. So remember that we are now in polar coordinates. So your phi is c theta. So it is expecting us to use the equations in polar coordinates. So let us see how we can solve it. So obviously it's given as a stress function. So if something is a stress function, we know what are the expressions for sigma r, sigma theta and tau r theta that have been already arrived at. So let us go to that. So going back, you have, I think it's page number 71. Yes, 7 yes, 56 on the second edition. So these are the expressions. So if phi is a stress function, sigma r is given by 1 by r del phi by del r plus 1 by r square del square phi by del theta square. Sigma theta is del square phi by del r square, and tau r theta is 1 by r square del phi by del theta minus 1 by r del square phi by del r del theta. So again, one thing you have to note is that these expressions are assuming that body force is 0. Okay, so in this problem also we can conveniently assume that body force is 0. Okay, now going back to the question once again. So you are asked to make you are asked to determine the details of such a stress function which is given by c theta. So let us arrive at the expressions for sigma r, sigma theta and tau r theta. So I have my handwritten notes here. So these are the expressions for sigma r, sigma theta and tau r theta. So here you have a stress function which is very simple, a constant multiplied by theta. So you can pull out the individual terms. So del phi by del r, del square phi by del r square, they are 0. It's independent of r. Del square phi by del theta is c, and second derivative is 0. So now substituting these these two and these two into the expressions, you will get sigma r equal to 0, sigma theta equal to 0, and tau r theta is the only non-zero expression because of del phi by del theta. So you substitute it here. So first expression will be non-zero. So that's what we are seeing here. So c, so the constant c divided by r square. So this is in the so this is the expression for sigma theta and tau r theta. Now the question is asking you to apply it to a ring, annular ring as well as an infinite plate. Now infinite plate problem, it is actually dealt in a separate section in Timoshenko. So that's out of syllabus. So infinite plate, it is in page 112. So let me go to that. On top it's 126 here. So the case of an infinite plate is dealt within this section. That's not part of syllabus, so we won't take that up. Okay, now also coming to the second part of the question. Now okay, this ring with annular ring, we will discuss it, we'll take it up, don't worry. So second part of the question, what it is saying is that a ring is formed, a ring is fixed at r equal to a and subjected to uniform circumferential shear at r equal to b, forming a couple. using some equations, you have to find the expressions for displacements. Now, the shear and equivalent couple and finding displacements, those aspects are also out of syllabus. So I given the page numbers here. Those who are interested can look it up. Of course, some parts of determining determining the displacement, we had used that in the derivation for plate with rotating disk, a rotating disk problem when we solve that. But the intermediate step as it is, I'm not giving a weightage for that. So this part also we can neglect it, saying that it's not part of syllabus. So the only part of the question which we'll solve is how these stresses relate to a ring. Okay, so that's what we had seen earlier. So that part we had seen towards the beginning, when immediately after arriving at the expressions for equations of equilibrium as well as stress function in polar coordinates. During our class work, we had solved this problem, right? We had solved the problem of a annular disk. But here when we had solved problems which are independent of r and theta and things like that. So now let us look at how these stresses relate to a annular disk. So you are asked to apply it for an annular disk with an internal radius a. So this is like a ring, right? Ring with internal radius a and external radius b. Exactly similar to what we had seen in the class when we discussed the other part. So this is a and this is b. So here, as we said, second part of the problem, we won't take it up. Okay, it is like you are applying a uniform shear and things like that. But to have some, more insight, let us assume this condition. So let us assume a annular disk with radius, internal radius a and external radius b, which and as is told here, let us assume that it is fixed at r equal to a, which means there is a fixity inside the annular inner radius, and external radius is subjected to a constant circumferential shear. Okay, how that relates to couple and all, don't take it up. So let us assume you have a annular disk, internal radius a, external radius b, and it is subjected to a shear s. Now we know that sigma r and sigma theta is 0 anyway. So strictly speaking, you also cannot have a boundary condition which is having a non-zero sigma r, because it is 0. Okay, so this is the only possibility. So for this possibility, if this is the case, tau r theta is given by this expression. So here c is a constant. So to evaluate the constant, let us put the boundary condition. So boundary condition is that there is a circumferential shear of s at radius b. So at r equal to b, tau r theta is s. So this is tau r theta is basically shear stress. So here it is also s. So you substitute that c is s b square, and you substitute that, you will get tau r theta is s b by r whole square. So this much is all that we can do with this particular problem. So only thing that we did is, using the stress function, we found out sigma r, sigma theta and tau r theta. And to make sense of the equations, as an extra, we did something like this. Now to also just to give you a little more insight, let us also try to plot this in Excel and see whether it will interest us a little more. So I have Excel sheet open with me. So let me just try to draw an annular disk. Yes, this is the one. Let me just increase the size a little. Yes. So assume this is our annular disk. Let me just mark arrows to show the radius. This is the inner radius, and you have the outer radius. Let me just change the color of that format. Let me just give something like yellow. So inner radius A is A, let it be some value, let it be, say, let's take it as 4. Of course it can vary, so let me just give it a fluorescent color. Similarly, outer radius, let it be something like, so outer radius is denoted by B, let it be some other value, 12 or something like that. Now it is subjected to a constant, so inner radius is fixed, external radius is subjected to a constant shear S. So let me consider the radius S. Let me give a value of 50. It can vary again. So units I am not specifying. Now this is the expression for tau r theta we had arrived at, right? So let me just try to plot this. Okay, so to plot that I need some points. So let me take points as a fraction, 0, 0 0.2. Let me take 5 or 6 points here. Okay, so this is inner radius, again function f4, plus outer radius, again function f4, so that it will remain static when I scroll, minus inner radius function f4 into this fraction. Okay, so this is uniformly varying, so inner radius is 4 and maximum radius is 12. Okay, so that is the radius. Now let us put in this particular expression, xs into b by r whole square. So this is equal to, this is s, again function f4, we want it to remain static, into bracket b, so 1 second, b by r square. So b also we want it as static, so function f4 by radius shift square. Okay, so these are the values, right? Let me just reduce this. So these are the values, so let me just plot it. So this is radius and this is tau r theta, tau r t, just so let me just plot this, insert, yes, maybe I'll change the chart type, yes, yeah. So here let me just fill let me just change the fill of this. Let me just give it a green color, move it to this side. Let me change the transparency of this format. Okay, now let me remove the outline. So format chart area, no fill. Okay, so that you can view it transparently. So it is like you are seeing in real time, right? So this is the this is the stress. So at r equal to 12, so you can imagine it like, you know, the variation of tau r theta along the thickness. So at r equal to b, which is 12, it is 50, which is our initial boundary condition, sorry, and at r equal to 4, it is 450, which is shown here. Now if you play around with these values, obviously the values in the graph will change and the tabular values also will be scaled down accordingly. Okay, So this was the problem. It's actually a simple problem. The Excel part and all was just an addition. So if you have any doubts, please let me know. Thank you.